Alright, so here's a video on understanding some parent functions. These are the core functions that you expect to know, what they look like, domain range, how to graph it, understand the equation, and so on. So just look at each one individually, and we'll fill it in. This is going to be a great reference sheet, because when you forget, which we do, you have something to go back to remember what it looks like and what some of the key attributes are. So first, what does the equation look like? So we can see a linear. The equation you're looking at is just y equals x. The domain and the range are all real numbers. The x-intercept and the y-intercept for this one you can see is 0, 0. There are no critical points. It's strictly increasing. The end behavior, as x approaches infinity, the function also approaches infinity. As x approaches negative infinity, that's the left end, the function also approaches negative infinity. So the right end's going up and the left end's going down. Any discontinuities? Nope. Is it even or odd? Good question. It's definitely an odd function in terms of the across the origin. Perfect. Next one. Absolute value. So what does the picture look like? Like a V. The domain is all real numbers, but the range here actually goes from 0 to infinity. So there's the bottom. Is there an x-intercept? Yep. And is there a y-intercept? Yep. At 0. Is there any critical points here? And we do have a local minimum, right? Actually, like an absolute minimum. And so the 0, 0, so 0, 0 is the vertex of this. Where is it increasing and where is it decreasing? So increasing from 0, and it goes to the right. It's increasing from 0 on. Where is it decreasing? Left to right. So from negative infinity to 0, it's decreasing. What's the end behavior here? So as x approaches infinity, what does the function approach? Also infinity. As x approaches negative infinity, what does the function approach? And you can see it also approaches infinity. The left and the right end are going up. Any discontinuities? Nope. Is it even or odd? And you can see this is an even function as it has a reflection over the y-axis. Quadratic. You can see the picture. We call that a parabola sometimes. Oh, I didn't even write down the equation for the parent for absolute value. So it's the bars, right, that tell us. For the quadratic, it's y equals x squared. The domain is all real numbers. The range goes from 0 to infinity. The x and the y-intercepts are at 0. We have one extreme point. That's the absolute minimum at 0, 0. Where is it increasing? This is just like the absolute value function, right? So from 0 to infinity. Where is it decreasing? From negative infinity to 0. What's the end behavior? As x approaches infinity, what does f at x approach? The function also approaches infinity. As x approaches negative infinity, what does the function approach? Also infinity. So both the left and the right end are up. Any discontinuities? Is it even or odd? And you can see just they match, right? That absolute value in quadratic, just the shape looks different. Parent. So this, what you're looking at, is called the cube function. That's y equals x cubed. The domain is all real numbers. The range is all real numbers. Is there an x-intercept? It's at 0, 0, and a y-intercept at 0, 0. So in terms of extrema, there's none, but there is a critical point here. And the critical point at 0, 0 is called a point of inflection. Notice it frowns and then it smiles, and right there is where it changes concavity. Where is it increasing? From negative infinity all the way to positive infinity. The whole thing is increasing left to right, and there's nothing that's decreasing. Oops. There it is. What's the end behavior? Well, as x approaches infinity, f at x approaches infinity. As x approaches negative infinity, what is the function approach? Also negative infinity. That's a fancy way to say the right end goes up and the left end goes down. Any discontinuities? Nope. Is this even or odd? So you can see it. It is an odd function as it has symmetry around the origin. Turn the page. Next one, square root. The domain here, so this is y equals the square root of x. The domain here goes from 0 to infinity, so we have no negative numbers. The range does the same thing from 0 to infinity, so no negative answers. We have an x-intercept at 0, 0 and a y-intercept at 0, 0. This point down here is an absolute minimum. So the absolute minimum is at 0, 0. Where does it increase? It increases from 0 to infinity, and there's nothing that decreases. What's the end behavior? So the right end, so as x approaches infinity, the function is approaching infinity. The left end, as x approaches, and we wouldn't say as x approaches negative infinity. It really doesn't have a left end behavior because it won't approach negative infinity because you can't have negative numbers. So I'm just going to leave it at that. The right end goes to infinity. The left end stops, right, at 0. Is there any discontinuities? Nope. And this one actually is neither even or odd. There's no symmetry here to go with for the square root function. Cube root. That's y equals the cube root of x. There it is. The domain is all real numbers, even though you don't think it would be. It is. And the range is all real numbers. So you can put a negative number under that radical sign. It's not a square root. Even roots you can't. But odd roots, you can have a negative number under the radical sign. We have x and y intercepts at 0, 0. We only have this point in the middle. Again, we have a concavity change. So at 0, 0 is a point of inflection, but we don't have a maximum or a minimum. The end behavior, where is it increasing? Everywhere from left to right. It's going up, left to right, and there's nothing decreasing. End behavior, as x approaches infinity, the function approaches infinity. As x approaches negative infinity, the function approaches negative infinity, which is the fancy way of saying the right end is going up and the left end is going down. It's just going up and down slowly, but it's still increasing, just not rapidly. You can see the smile compared to the frown. It's the concavity there. Any discontinuities there? Nope, it's continuous all the way through. Is it even or odd? And you can see it is an odd symmetry around the origin. And one way to tell whether it's odd is by looking at the cross quadrants. So quadrant 1 and quadrant 3, or quadrant 2 and quadrant 4. Seeing symmetry in the quadrants that are across from each other gives us that odd symmetry. Next, reciprocal. Sometimes we call that reciprocal a rational in terms of this. So this is the simple rational, which is a reciprocal. The domain of that is all real numbers, and I'm going to write it like this, but x can't equal 0. Same thing with the range. It's all real numbers, but y can't equal 0. I could write it in interval notation. It's just quicker to write it this way. There are no x-intercepts and there are no y-intercepts for this. It doesn't touch or cross the x or the y-axis because there are asymptotes that are around it. Where is it? Are there any extreme points here? None. Do you see any intervals where it's increasing left to right? And so both are actually not increasing but decreasing. So the whole function is decreasing. And then technically we would separate it at 0 because it's not continuous there. So from negative, we have two pieces. So we have two intervals. So from negative infinity to 0 and from 0 to infinity, both are going down left to right. What's the end behavior? So the right end and the left end behavior. So it's going to be a little different. So as x approaches infinity, I need to know that x, the function f at x approaches 0. And as the function, and as x approaches negative infinity, the function also approaches 0. So notice in this case, it's not going to infinity or negative infinity, but actually gets closer to 0. Any discontinuities? Yeah, at x equals 0, what do we have? Is that vertical asymptote? Is this even or odd? And again, look at the cross quadrants, and you can see there's symmetry with that in the top right and the bottom left. Exponential. And of course, if you ever feel it's going too fast for you to make notes, that's why it's a video. You can press pause. All right, exponential. The domain for an exponential is all real numbers. They all work, but the range goes from 0 to infinity, and 0 is not included. That's why there's a parenthesis around 0. X-intercepts, there's none. It doesn't touch or cross the x-axis, but we do have a y-intercept at 0, 1. We have no extreme points or critical points, so there's none there. Where is it increasing? Everywhere. So from left to right, it's going up, and there's nothing that's decreasing. End behavior, as x approaches infinity, what's the function approaching? Infinity. As x approaches negative infinity, what's the function approaching? And the answer is 0. So the right end behavior is infinity, and the left end behavior is 0. Any discontinuities? Nope. Is it even or odd? And the answer is neither. So whether across the y-axis or across quadrants, we don't have symmetry with an exponential. Turn the page. Next is a logarithm. So we can think of this as y equals log x. The domain of that goes from 0 to infinity. The range is actually all real numbers. It goes forever up and forever down. There is an x-intercept at 1, but there's no y-intercept. So here it crosses the x, but it doesn't touch the y-axis. Any extrema? No. Is it increasing? Yep, everywhere. From negative infinity to positive infinity, it is increasing. Well, not from negative infinity, sorry. From 0 to infinity. So from 0 to infinity, it's increasing. There's nothing that's decreasing. What's the end behavior? So where's the right end and left end going? So as x approaches infinity, the function is approaching infinity. As x approaches 0, the function is approaching negative infinity. Any discontinuities? Nope. Is this even or odd? And the answer is neither. This is a unique one called the greatest integer. Sometimes it's called a step function, because can you see the steps going up? So the symbol for that is a double bar. So if you have a double bar, sometimes the double bar even has look like double brackets, but it's a double bar. The domain for this is all real numbers. The range for it are all integers. So you can't have a fraction or a decimal answer. So it can be negative or positive, but they're all integers. The x-intercept is at 0, 0, and so is the y. There's no critical points here. Where is it increasing? So as you look left to right, you can see that it's increasing going up, but there's also constants in between as it's increasing. So it's a little bit awkward to understand increasing and decreasing. What's the end behavior? The right end and the left end. So eventually this is going to go, as x approaches infinity, the function approaches infinity. As the x approaches negative infinity, the function is going to approach negative infinity. any discontinuities, and there's a jump at every integer. So is this even or odd? And the answer is neither. So to put a better perspective into this, whatever number you put in here, so let's say if I looked off the graph and you said I'm going to put in 1/2, you would actually go to the integer, and how it's said is what's the greatest integer less than or equal to whatever number you came into. So you're going to go backwards. So for 1/2, what's the greatest integer? What is it closest to going back, going less? And so for 1/2, the closest integer to 1/2 that's less than or less than or equal to what the number you put in, that would be 0. So just like if you put in a number between 1 and 2, you'd work back to 1. Between 2 and 3, you'd work back to 2. And I know it says the word greatest, so it feels like you're going to bump up, but actually it works the other way. So whatever number you put in, if it's an integer, then it is what that integer is. But if you put a number between two integers, it always bumps back to whatever that closest integer is. All right, sine, some trig waves. What's the domain for sine? It's all real numbers. What's the range? It goes from the bottom to the top of the wave, which is -1 to 1. Intercepts are at 0 for both. The extreme, well, where do we have extreme points? So if you like to think of it in terms of it, so we have it oscillates, right? Top and bottom, top and bottom. So if you like to think so we have extreme at all over the place, right? Because it oscillates. To create those extrema. Where is it increasing and where is it decreasing? Same idea, that it's constantly increasing and then decreasing and then increasing and decreasing and so on. So I'm not even going to worry about filling this out as much. Where's the end behavior? It doesn't exist because it just keeps oscillating up and down in terms of what's happening. So you can see that we have moments of increasing from -π/2 to π/2, or from π/2 to 3π/2, it's decreasing. I don't even have enough space to try to fill that out, so I'm not going to worry about it. It's continuous. Is it even or odd? That's a good question, actually. So when I look at sine, look at the cross quadrants, it's actually an odd function, sine. That might be the most important part in terms of the analysis to understand it with calculus. We'll compare that to cosine. So almost the same analysis in terms of it. It's all real numbers, goes from -1 to 1. The x-intercepts are different. So the x-intercepts are all over the place. We don't have one at 0, 0. I mean, there's definitely one at π/2 and 0, but they're all over the place. The y-intercept is just one of them. And that one where it crosses the y is at 1. And that all over the place. It just keeps oscillating up and down. Interval, same thing. I should call it AOP, all over the place. AOTP. I'm not going to list each one or say it generically for you, but the end behavior, again, it doesn't exist because it oscillates. There's no discontinuities. But here, I want to get to here. See the reflection over the y-axis? The big difference between sine and cosine has to do with symmetry. Sine is odd, and it starts in the middle. Cosine's even, and it starts at the top of the wave. Big, big. That's the difference between the waves. All right, turn the page. Now the question is, can you take these parents and can you transform them? So some language to begin with in terms of what's happening. When something is transformed down, and when we have something transformed down, we call it shift, and we call it a vertical if it's going up or down. And so whatever the function is, it's being transformed down if you subtract on the outside. If you add on the outside, it's going up. How about left and right? We call it a shift, but left and right we call it a horizontal shift. You might remember this is inside, and it's the opposite direction on the inside. Oh, we call this H. Think of it as HK form. H and K. How about if you had a reflection? Well, it reflects about the x-axis. The negative is on the outside. If it reflects it on the y-axis, the negative is on the inside. So when I see negative signs that weren't there before, that's a sign that there's a reflection. Is the negative outside the function or inside the function? Next, dilation, sometimes more often called compresses or stretches. A compression means it got smaller. A stretch means it got bigger. So when you have vertical compressions and vertical stretches, understand that whatever the number is in front. So if I have a number being multiplied in front, if that number is between 0 and 1, like a fraction, it's going to compress it. If I have a number in front of the function is being multiplied and that the absolute value of that number, so if it's negative, it belongs to a reflection. But just the number without the negative, if that's greater than 1, and this should also be an absolute value sign. So if you have a number bigger than 1, regardless if it's negative or not, it creates a stretch. Now, the compression goes the inverse of that, right? So if something's being multiplied inside, we'll call that B, that if that number on the inside, if you took the absolute value of it and it was bigger than 1, it could form a compression. Notice it's the flip, right, in terms of what happened vertically. If we have that same idea, something multiplied inside and the absolute value of that is between 0 and 1, that's what's going to create a stretch. So when you look at it, horizontal compression is actually the same as a vertical stretch. They do the same thing to the graph. So if you squish it in horizontally, it actually creates a vertical stretch. If you stretch it out horizontally, it actually creates compression vertically. So they work inversely. So the function will compress or stretch vertically by a factor of A, and here it would be 1 over the reciprocal of what you see. So 1 over B. All right, turn the page. Now let's actually practice. Can you, given the function, identify the parent and the transformation for it? So when I see the parent here, the parent is y equals x cubed. And what happened to the parent? And it's a vertical shift down 4. So I look and I see subtracting outside of it. For a cube function, inside you'd have to see parentheses. Number 2. So what's the parent? So the parent is y equals the square root of x. So the parent is the simplest form without any adding or subtracting numbers of any sort. There are a bunch of different transformations. So I'm going to start using acronyms to help me. So what's on the outside affects the y. It's vertical. So it's actually a vertical stretch by 2. Inside, I see a negative sign, so that means it reflects. And when it's on the inside, it reflects about the y-axis. And then I see, and I'm going to do the inverse of what I see. So then I see a horizontal shift. And the inverse of what I see, the opposite direction, is to the right one. Number 3, what's the parent? So it's just x squared is the parent. And there's a bunch of stuff happening to x squared. So what's happening to it? So what's on the outside? I see 2 things. So the negative on the outside creates a reflection. So it reflects about the x-axis when it's on the outside. Also on the outside I see plus 6, which means there's a vertical shift up 6. And when I see the inside, I do the inverse of what I see. So that's actually a horizontal stretch on the inside by 4. So the inverse of that times a quarter is times a 4. or the inverse of dividing by 4 is multiplying by 4. All right, number 4. What is the parent? And what do you see? So on the outside, I'll look first. That's a vertical shift down 2. On the inside, I see a horizontal compression, because it's the inverse, of 1/3, because we have to do the inverse of that. And then I see a horizontal shift. And what direction is it going? Left. How many? 5. Your turn. Try number 5. Parent is just x squared. Anything on the outside? Yeah, so it creates actually a vertical compression because it's going to get smaller by 1/2. Do you see anything on the inside? So it's direction. So it's a horizontal shift, but what direction? To the right 6. 6, what do I see? I see a fraction with a variable on the bottom. So the parent is that rational function, reciprocal, 1 over x. What do you see on the outside? I see a negative and a +3. So it's going to reflect about the x-axis, because it's on the outside. What else do I see on the outside? I see adding 3. So that means it's going to go up 3. And then what else do I see on the inside? So inside the fraction, I see a 4. So I now have to do the inverse of what I see. So instead of times 4, it's actually a horizontal compression. And I'm just looking at the 4, so the inverse of that is 1/4. Number 7, what's the parent? That's the cube root of x. What's happening on the outside? Let's start there. I see a negative, so it's going to reflect about the x-axis when it's on the outside. I see a 4 and a 2, so we have a vertical stretch by 4. We have a vertical shift up, how many? 2. And then one more on the inside, I see a horizontal shift the opposite direction, so left, how many? So can you analyze the transformation? Identify the parent and do it. So this one's called a greatest integer function, that's that double bar. What's happening inside and outside? So start on the outside, so there's a vertical shift down 1. And on the inside, 2 things are happening. So I see a subtract 5 and a divide by 2. So the subtract 5 means the direction it's going is to the right. And then the divide by 2 actually becomes a horizontal stretch. And it's going to go by 2 instead of the divide by 2. Number 9, can you identify the parent? So the parent is the absolute value of x. Anything on the outside? Yep. So there's a vertical shift up 7. Inside, there's 2, 3 things happening. So I'll just go one at a time. So it reflects. When it's on the inside, it reflects about the y-axis. What else do I see? 1/3. So the inverse of that, that's times 3. So it's actually a horizontal stretch by 3. And then one more. What does that subtracting 4 do? It makes it shift. And what direction is it going to shift? To the right. That's right, to the right 4. 10. What's the parent? Y equals x cubed. So what's happening on the outside and what's happening on the inside? So start with the negative that you see. That means it's going to reflect. Which axis on the outside? So it's the x-axis. So when it's on the inside, it's the y. The negative on the outside is the x-axis that it reflects. 3 divided by 2 is a fancy way to say 1.5, so it's a vertical stretch. I'm just going to use 1.5, which is the same as 3 over 2. And then one more, there's a vertical shift. What direction does it shift? Down, how many? 8. And then on the inside, there's a horizontal shift. In what direction is that going? Left. How many? 3. Excellent. All right, turn the page. Let's do one more together, and then there's a homework sheet. I'll do that on a separate video. So, do you have the ability to use the graph of the function, identify the parent, then write an equation for the function under each transformation? So, if I look here, what's the parent? It looks like a v. So which function has that? So that would be the absolute value of x. If you're going to translate it to the right, is that inside or outside? So I'm going to rename this with a 1. And if it's going inside, it's actually going to subtract because it's the opposite direction. If it reflects on the x-axis, that's outside. And if it goes up 5, that's also on the outside. Done. So it's just practicing. When you identify it, can you see it? So the parent there, I'm just going to call it y equals 1 over x. So if I translate it 7 units down, that's outside. 3 units left, that's inside. So how can we put it together in a smart way? So I'm going to call this f1 at x. So on the outside, it's going to go down 7. And on the inside, it's going to be inside the fraction. And it'll actually be the denominator of the fraction. And we're going to add 3 because it's the opposite direction. Oh, there's a C right here. Like everyone. Anyways. How do I do this? Horizontal stretch by 3 and translate 2 units to the right. So I'm going to call this f2 at x. So again, it's a fraction. The easy part is, well, actually, there's nothing happening outside. So horizontal and 2 to the right, all is inside. And when it's inside a fraction, it's actually the denominator. So if it's a factor of 3, we do the inverse of what I see. So it's actually going to be 1/3. And then we're going to translate this 2 to the right. So that means I'm going to subtract 2. So instead of 3, it becomes 1/3. Actually, it's a horizontal stretch, right, of 1/3. Good. So I have to do the inverse when I see it. So when I see times that number, that creates that horizontal stretch. Parent, this is the greatest integer function, the double bar. Can you go 1 unit up and then vertically stretch by a factor of 4? So when it vertically stretches and goes up, it's on the outside. So a vertical stretch by 4 means you multiply it on the outside by 4, and then up 1 means you just add 1 at the end. Vertically compress by a factor of a third. So that would be 1/3 in front, and then 6 units left means inside you would add 6. A parent function, that's a cube root. So if I take that cube root and reflect it in the y-axis, that's actually on the inside, and then translate it 4 units right. So I have this. I need parentheses to do this on the inside, and then it's the opposite of what I see. So I'm going to subtract 4. So the negative reflects, and then the parentheses allows me to do the opposite, to go to the right 4. One more time. Horizontally compress by a factor of 1/2. And then translate 5 units down. So I have a cube root. I do the inverse of that. So instead of dividing by 2, I go times 2. And then translate 5 units down means outside the radical sign, I'm going to subtract 5. If this function is reflected across the y-axis, That's inside. Then translate right 6 units and down 2 units. Write the equation of the new function. So we have a few things happening here. So I have a new function, I'll call that 1. It's going to reflect, then it's going to translate right 6 units and down 2 units. So first of all, if it's the y-axis, it's on the inside, and then I need a parenthesis for that. And if it's going 6 to the right, -5, 6 to the right, we do the inverse, so we subtract 6. So -5 subtract 6 gives me -11. And then if it goes down 2, you take the 3 and subtract 2, and now you've subtracted 1. Kind of the next Yoda level of doing this. 16. A function was vertically stretched by a factor of 2, then translated 2 to the left, 5 units up. The resulting function is represented below. Write the equation of the original. So go back to what it must have been before that happened. So now, it's going to give you a brain trippy here, but if it's stretched by a vertical factor of 2, I got to go back to what it was. That means I got to divide by 2. So if it was 3 originally, and then you stretched it by 2, 3 times 2 then would give you the 6. If it went 2 units left and end up here, well, I have to actually subtract and go, okay, it must have been 2. And then 2 units left means you would add 2 and get the 4. And then 5 units up, it must have been -6, because if you go 5 up from -6, you get the -1. Again, this is the next Yoda level, becoming a Jedi to do with transformations. All right, so now's the time for you to practice that. I'll do a new video. You can actually practice with me if you like.